All right, so let's work on this one. Now, this is another pretty simple frame one that has two components. This is a little tricky. It's hard to see here, but this is just like a roller support. It looks like the frame is allowed to slide in the X direction, but not in the vertical direction. It's fixed at B, and then over here at C is a pin. So you can, again, draw a single free body for the whole structure and find your reactions. And we'll do that to get started.
These will be labeled on the test, right?
If it's on the exam, if it's not obvious, then I'll tell you. Assume like you might look at this when you say, "Is that a fixed connection? I can't tell." So I would tell you that it's a pin.
Thank you.
Now, here's another piece of logic that you could apply. If this were fixed and this were just a roller, could we solve this problem? Answer is no.
You have 4 unknowns.
Because we would have 4 unknowns and only 1 free body. And this is a fixed connection, so I can't take it apart there to help me.
But if it was a pin, we could.
Since it's a pin, there's only 2 unknowns at a pin and 1 at a roller. Now we have 3 and 3. We're back in business.
Or if B was a pin, C was a pin.
Yeah, but that I think you can see even from this diagram, that's not a pin.
No.
I would just...
So a lot of times I understand. I think if you actually had this problem and you looked it up in your book, the author would tell you, and I usually leave that out here and we talk about it, but he would tell you that this is a roller and this is a pin. It doesn't really leave it up to you to choose. Okay, so with that as a background, then I'll go ahead and assume that I have a Y reaction at A and one at C in both the X and Y directions. And then we'll go from there. So, like we've done a few times this semester, we will sum moments about a pin. Maybe in this case C. And we'll make sure it's in equilibrium. Before we get too far, let's resolve this distributed load into something that's a little easier to handle. So we'll turn it into a concentrated equivalent force. And it's a rectangle, so we just need to find the area of that. So the base is 4 meters. The height is 3 kilonewtons per meter, so that's 12 kilonewtons. And that'll be halfway, so that'll be either 2 meters from the top or the bottom, whichever one we need. So we should have enough information to make sure that the moment sum is 0. So about C, both these forces create what kind of moment about C using right-hand rule? Positive. So I'll start with the first one. So I've got 24 kilonewtons as the force. There's my moment arm, 3 meters. Then I've got my concentrated equivalent force, 12 kilonewtons. And then from the line of action of the force will be this half distance, which will be 2 meters.
Are they positive or negative?
They are both positive. Thank you. Now the moment due to the reaction force AY is going to create negative. So there's the force AY, which we don't know, and its moment arm is this distance, which is 6 meters. So let's solve for AY. And 12, 18, I'm guessing. What do you guys get? 16? I guessed wrong, I guess. 12, 2, 4, 12. Yeah, what's 12 and 4? 16? Everybody agree? No one's playing along now? You guys all watching Fuzzy Cat videos out there? What's going on? I know it's pervasive in our society. My 7-year-old called me away from my very exciting football game last night, which it was not, and said I had to come see something. It's the funniest thing he's ever seen in his life. He's crying. He's laughing so much. And he shows me a cat that's singing Happy Birthday. And it's like, what the? He thinks it's the greatest thing in the world. He goes, I love YouTube, he said. I said, what about your dad? Nah. I love YouTube. I turned off the router immediately. I just went and hit the off button, click.
Go read a book, kid.
Have you seen In the Deer tonight?
I don't watch TV.
No, it's a
I'm not familiar. I don't interact with computers at all.
You would like that one.
Okay, enough of that. I just thought I'd tell you that. It popped in my head. I don't have self-control. So let's sum forces in the y direction. So look in the y direction, I have AY acting up. I got CY acting up, so those will both be positive for me. What else is in the y direction? Oh, this 24 is acting down. So it looks like I can solve for CY. Looks like it's going to be 8. And then last, we'll check the x direction. So I'll assume to the right is positive. And I will sum forces in the x direction. And what do we get? Well, I've got CX is to the right, so that's positive. And I've also got this big horizontal load here. The concentrated equivalent is 12. And that's also to the right, so that's positive. So CX is opposite that to balance it. So I've got my reactions. That seem reasonable?
It does seem reasonable.
Seems reasonable. Okay. So now what?
Split them up.
Split them up. So now it's. I guess in this problem you can either decide to look at AB or BC. I don't think there's much difference between them, but I think I'll look at BC just because. So if I look at section BC, now I was trying to examine them quickly to see if there was any advantage to either of them. They look about the same. So this one was already drawn in the horizontal direction. Seems like a kind of a lame rationale, but that's what it is. So I'm just going to transfer my information there. And I've already found my CY value. I know it's in this direction, and it's equal to 8 kilonewtons. And I've already found my CX value. I know it's in this direction, and it's equal to 12 kilonewtons. So now at B, I'm going to make my assumptions. And I'm going to assume that I have a force BY up, Bx positive, and since I'm doing right-hand rule, I'll say my moment in B is in this direction. And I'll worry about what's shear and axial force and bending moment and all that later. So this is all for the unknown things. Again, it's always a good idea to sum here. Not only do I eliminate Bx, By, I can solve for the moment at B, and we'll do that. So let's sum moments at B. Make sure it's in equilibrium. So about B, this 24 kip force creates positive or negative moment.
Negative.
Oh, I'm sorry. Let's do this first. What about my moment at B, positive or negative?
Negative.
Well, I'm using right-hand rule, so it's positive.
Oh.
It's a negative bending moment, but we're not doing that yet. So what about the 24 kip about B, positive or negative? Negative. And moment arm is 3. Are you guys in on this? Is it just too boring? Or are you still having questions about that? Because this is something kind of needs to be worked out pretty soon. If it's not, we might have to just pause and have like a big group problem. No? Maybe we'll pause later and have a group problem. All right, so what about this 8 kilonewton force about B? Positive or negative?
That's positive.
Oh, wow. We're outspoken. And moment arm is 6. What's the moment created by the 12 kilonewton force about B? Wow. That is correct. So what is the moment at B? 24.
Yeah.
And it is positive?
Yes. Yeah. Yes.
Yes. Okay. What else do we need to find? Let's find some forces in the y direction first. No particular reason to do that, but I will. So Bx is up. That's positive. 24 is down. Consider that to be negative. 8 kips is up. I consider that to be positive. Anybody else left? I think that is all. So therefore, By is equal to 16 kilonewton. Positive. I didn't leave myself room down here. I don't think I can squeeze. Well, maybe I can squeeze it in. I'll write smaller. So we will now sum forces in the x direction and set that equal to 0. So I've got Bx, which is to the right, so that's positive. And the 12 kilonewtons, which is to the left, which is negative. So it looks like Bx is equal to 12 kilonewtons. Sweet. So what I'm going to do is I'm just going to redraw over here and put all my components back on. So here's the section BC with the original 24 kilonewton load applied. And we have found that CY was 8 kilonewtons and that CX was to the left equal to 12 kilonewtons. We've just solved for Bx, which was in this direction, and we solved for By, which was up, and we solved for the moment, which I drew. Didn't leave myself much room. I'll do it like that. So we've got a positive value of 24 kilonewton meters. So that's all that's happening on BC. Then equal and opposite to that should be what's happening over here on AY. We found AY to be 16 kilonewtons. And of course, along the edge, we have a distributed load which has the value of 3 kilonewtons per meter, and that was 4 meters. I left off the dimensions here. I'll put those in. And then equal and opposite, so that means that this one comes in at 12 kilonewtons. These are opposite. This one is opposite. It's down 16 kilonewtons. And this guy is this way, 24 kilonewton meters. Kind of jam that in there. Maybe I'll put a little squiggly line to show you the difference of the two.
Good call.
So you see it all kind of fits back together. So now we can take these components and use them to draw the shear force and bending moment diagram. So I'll move that out of the way. I will show you that, to do AB, I'm going to rotate it and look like this. That's the way we'll do it today. Oh, I got stuck. So let's redraw that. I'll start here with what I know on AB. That is the distributed load. And now I'm only going to be concerned with the shear force and the bending moment. So there is no shear force at A, remember? The way we're doing it here, there is no shear. At B, there was a force equal to 12 going up. And then there was a moment in this direction equal to 24 kilonewton meters. Oh, I left this off. This was 3 kilonewtons per meter, and this was 4 meters total. So I think that's everything I need. I'm not worried about the axial force in this particular element, which was 16. I think that's it. So let's start with our template. We'll go left to right. There's the length of the beam. Establish our positive x-axis. Positive shear, and all of the shears will have kilonewton for the unit. So what is the shear at A? Zero. What is the shear at B? Negative 12. We know from our work that the change in shear is equal to the area under the load, and that the slope of the shear diagram is equal to the load. So let's do the change in shear first. What is the area under the load curve here? What's rectangle base 4 times height 3? That's 12, and it's down, so it's negative. So if you start at 0 and you subtract 12, you get minus 12. That's nice. And then the slope of that curve should be given by the load. The load is constant and negative. So here's my constant negative slope. So now we'll go and do the moment diagram. So again, we'll establish positive x-axis, positive moment, and we'll do kilonewton meter for all our values. What is the bending moment at A? 0. What is the bending moment at B? Negative 24, right? And we know that the change in moment is the area under the shear, not the W, the shear diagram, and that the slope of the shear diagram, did it again, the moment diagram is the shear. So what is the area of the shear diagram?
24.
Yeah, it's a triangle, so 1/2 base 4 times height. And what do you know? It's 24. So starting at 0, subtract 24, you get 24. What is the slope of the moment diagram at A?
0.
Why? Because the shear is 0. What is the slope of the moment diagram at B? Negative 12. So we can swag a curve, and there's my moment diagram. So now we can look at BC. In the middle of BC, we have the original 24 kilonewton load. The shear at B, let's drop back and look at our previous problem. That would be this value here, and that's up of 16 kilonewtons. And then CY was also up equal to 8 kilonewtons. I'm not going to worry about the axial force. There was no moment at C, but there was a moment at B, and it was in this direction and had the value 24 kilonewton meters. So then we can generate a quick template for that one. Beginning and end. Establish an x-axis. Again, positive shear. Units of kilonewton. What is the shear at B on BC? Is that positive or negative shear? Positive. What is the shear at C on BC? Negative 8. So we know that the change in shear is the area of the load diagram. What's the area of the load diagram from 0 to... Oh, I didn't write those in, sorry. That's 3 meters. So over the first 3 meters, what's the change? Nothing. Oh, I left out an important line on my template, that force. So it doesn't change, it stays to 16. And of course, we know the slope of the shear diagram is the load, and the load is 0. So there's my 0 slope curve. So I have constant shear over the first 3 meters. Then as I go from the left side to the right side, what's the change in shear equal to? Negative 24. So 16 minus 24 is? Negative 8. The change in shear over the last 3 meters is the area in the load curve. The area in the load curve is 0. So negative 8 plus 0 is negative 8. That's great. And then the slope is given by the load. The load is 0. 0 slope. So there you go. Shear diagram. So now let's do a moment diagram. Positive x. There's positive moment. Everything will be in kilonewton meters. What is the bending moment at B? What is this bending moment? Positive or negative? Negative 24. What is the bending moment at C? 0. The change in moment is the area of the shear diagram. What's the area of the shear diagram from 0 to 3? 3 times 16. What's that?
48.
So that's positive. So 24 plus 48, or I'm sorry, negative 24 plus 48 is 24. The slope of the moment diagram is the shear, and the shear is constant and positive. What's the change in moment over the last 3 meters? What should be the area of the shear diagram, which is base 3 meters times height 8. It's negative 24. 24 minus 24 is back to 0. Yay. What's the slope? Negative. And there's a negative slope. Not to scale, but there's your moment diagram. So where's the maximum moment in the section BC? Tricky question. Where's the positive bending moment in BC? Yeah, it'd be 24 happens right in the middle. Where's the maximum negative bending moment? That's exciting. You guys like that one? All right, any other questions? It's very testable. I like this one. It's very testable. Not this test.